Rajdeep, am I audible? So I can see our speaker has joined. Thank you, Dr. Parijata Majumdar, for accepting the invitation.
Thank you, sir, for welcoming me. Thank you.
So we will start shortly. So our Vice Chair, Rajdeep Ghosh, will introduce you to the participants, and then you can share your views and thoughts on the topic of the spiking neural networks, the future of
Thank you,
Ben's
sir, for
barrier.
welcoming me. Thank you.
Myself, Sabyasachi Mukhopadhyay, Chair of IEEE CSSBC IIT KGP, and
Hello,
apart from me
Shubhasaya,
and
you are not
Rajdeep, we
audible
have
actually.
another member that is Dhyoti Manak. Can you hear?
Hello,
Can you hear me?
Shubhasaya, you're not audible actually.
Hello. Ah, just a second. Let me check. Myself, Sabyasachi Mukhopadhyay, Chair of IEEE CSSBC IIT KGP, and
Hello,
apart from me
Shubhasaya,
and
you are not
Rajdeep, we
audible
have
actually.
another member. Can anybody confirm me?
Hello,
Yes, you are audible.
you're not audible actually.
From the audience?
Yes, you are
Okay,
audible.
thank you, Mr. Mukta, for confirming.
Hmm.
Thank you so much. Thanks for the confirmation. So apart from, thank you, Mr. Dr. Vishwaranjan for the confirmation. So apart from me and Rajdeep, there is another team member, Ms. Dyotima Nath. So she is the Secretary of IEEE CSSBC. Hmm. So we are doing this event in collaboration with the IEEE student branch, Kharagpur section. So Mr. Kumarjit Ray is basically leading this particular segment. Hmm. So Rajdeep, I think without further delay, we can start gradually. You can introduce Parijita Madam, and then she can start her talk.
So, is it visible?
Yes, ma'am. It's completely visible.
So
So, ma'am,
thank
we are
you.
not, ma'am. Just to let you know, we are not able to see the screen share. I mean, the complete slideshow. We are able to see the complete slides actually.
Is it visible?
Ma'am, the screen is visible, but we are able to see the slides. We are not able to see that slideshow. So, if you are
So, is it
doing dual
visible?
screen, I guess that might be a problem. It's completely visible.
So
So, ma'am,
thank
we are
you.
not,
Just wait a minute.
ma'am, just to let you know, we are not able to see the screen share. I mean, the complete slideshow. We are able to see the complete slides actually. Yeah, ma'am, it's now completely okay. The screen share.
Is it visible? Okay.
When the
So
screen
should
is
I start?
visible, but we are able to see the
Yes, ma'am.
slides. We
Sure,
are
ma'am.
not able to
Sure,
Yes,
see
ma'am.
that
madam. Kindly
slideshow.
go ahead.
So
Kindly go
if
ahead.
you are
So is it
doing dual
visible?
screen, I guess
Thank you,
definitely
Yes,
might
ma'am.
sir
be a
Yes.
and
problem.
Yes.
Rajdeep,
Completely
for
agree.
your. And today it is my
So,
very
ma'am,
first
we are not,
session
ma'am,
with
just to
Sure,
let
ma'am.
IEEE
you know,
and
we are
with
not able
all
to
the
see
expert
the
members
screen
present
share,
over
means the
here. I'm
complete
really overwhelmed
slideshow.
to
We are
see
able to
all
see
of
the
you
complete
here.
slides actually.
So let's start with spiking neural networks, which is the future of brain-inspired AI. So let us come across what is spiking neural networks. Spiking neural networks
Yeah, ma'am,
are
it's now
actually a
completely okay.
breakthrough in
The screen share.
artificial intelligence, which is
Okay.
specially
Okay.
inspired
When
by
the
the
So
screen
should
is
I
visible,
start?
but
event-driven
we are able to
and
see the
Yes, ma'am.
slides.
temporal
We are
Sure,
not
ma'am.
able to
Sure,
dynamics
Yes,
see
ma'am.
that.
of
madam. Kindly go
biological
ahead.
brain
So
Kindly go
systems.
if
ahead.
you are doing dual screen,
As
I guess
opposed to
definitely might be a
conventional
problem. Completely agree.
artificial neural networks, spiking neural networks
So, ma'am,
actually
we are not,
uses discrete
ma'am,
spikes
just to let you
to
know, we are not
process
able to see the
information
screen
allowing
share,
for
means the
energy efficient
complete
computing and the
slideshow. We are
native
able to see the
handling of
complete slides
sequential
actually.
and temporal data. So the main focus is on physiologically inspired mechanism like spike timing dependent plasticity. What is spiking neural
Yeah,
networks? Basic principle of using spiking
ma'am,
neural
it's
networks
now
are
completely
actually a
okay.
breakthrough
The
in
screen share.
artificial intelligence, which is specially
Ma'am,
instead
the
of
screen is visible, but we
continuous
are able to see the
Yes,
activation
slides.
sure, ma'am.
as
Yes,
Sure, ma'am.
madam.
opposed to
Kindly go ahead.
artificial neural
Kindly go
If
ahead.
you
networks.
are doing dual screen,
As
I guess
opposed to
definitely might be a
conventional
problem. Completely agree.
artificial neural networks. So the main biological inspiration
So, ma'am,
comes
we are not,
across. It is modeled after the
sure, ma'am.
to process information in the brain using different
Complete
action
slide
potentials
show. We are
and
able to see the
handling
complete slides
sequential
actually.
and temporal data. So how SNNs actually work? The main focus is on physiologically inspired mechanism like spike timing dependent plasticity. So let us come across what is spiking. It is often called the third generation of neural networks
Yeah, ma'am,
because
it's
it
now
mimics
completely okay.
biological neurons more closely than traditional artificial neural
When
instead
the
of
screen is visible, but
continuous
we are able
starts
to
with
see the
Yes,
initial
slides.
sure,
block
ma'am.
Yes,
Sure,
madam.
ma'am.
encoding,
Kindly go
where
ahead.
the first block
If you are doing
converts
dual
the
screen,
real
I
world
guess
data
definitely might be a
into
problem.
spike
Completely
frames.
agree.
Here, images, sensors, signals, audio, or biomedical data are transformed into sequences of spikes. The different common encoding methods are being applied over here, such as rate encoding, which actually where actually the information is represented by spike frequency, temporal coding, where the information is represented by spike timing. It is often called the third generation of coding is also
Yeah,
used
ma'am, it's
here,
now
where the
completely okay.
spikes are generated probabilistically. For example, brightening of text pixel starts where it is converted into higher spike frequency, and darker pixels, as opposed to brighter image pixels, are converted to lower spike frequency. So this is the first building block of spiking neural network, where the first step is input encoding, as I have already emphasized. The second one is spiking neural network architecture, as we can see in this diagram, which is the core processing stage. It first starts with the input layer, which is mainly responsible for receiving encoded spikes from sensors or data sources. Then comes the hidden layers, just like artificial neurons, where the spiking neurons processes incoming spikes through weighted synaptic connections. Then after that comes the output layer, where it generates output spike patterns that corresponds to classes or decisions. Unlike conventional neural networks, neurons communicate only when they fire a spike, making the computation event-driven. So this is the basic difference of spiking neural networks and conventional neural networks, where the neurons communicate only when they fire a spike, making the computation event-driven. The third one is spike decoding. Here, the output spikes must be converted into useful information, and the common decoding techniques that are applied widely over here are rate decoding, where the neuron produces the highest number of spikes being selected, the time to first spike decoding, where the neuron that fires the first determines the prediction. For example, the output neuron A fires 25 spikes. The output neuron B fires 12 spikes. So what is the result? The output neuron A predicted class A is being selected. Then comes the fourth step, the output, where the final prediction can be image classification, It can be disease diagnosis, it can be object detection, it can be speech recognition, or autonomous robotics control. Then comes the spiking neuron model, which is the leaky, integrate, and fire method. This section actually shows how a biological inspired neuron actually works. The step one is integration. Here, all the incoming spikes arrive through synapses with weights. The neuron accumulates these signals in its membrane potential. Then comes the leakage step, where the membrane potentially gradually decreases over time if no new spikes arrive. The third step is threshold checking. That is, when it crosses the threshold, the neuron emits a spike. Then comes the fourth step, that is reset. That is, after firing, the membrane potential resets. This mechanism closely resembles biological neurons. Then comes the spike timing dependent plasticity, where the case one is there are several cases in this. Presynaptic spike arrives before postsynaptic spike. The connection becomes stronger with potentiation. Case 2 is postsynaptic spike arrives before presynaptic spike. Then the connection becomes weaker, that is depression. This allows the spiking neural networks to learn from temporal relationships between data. Then comes the neuromorphic hardware mapping. Here, spiking neural networks are particularly suited for specialized hardware such as Intel Lohi, IBM True North. The advantages typically include low power consumption, event-driven computation, as I have already re-emphasized, real-time processing, massive parallelism between works, suitable for edge AI and IoT devices. So the most important concept of spiking neural network is that here information is being represented by discrete spikes, as I have already said, occurring over time rather than continuous numerical activations. Because neurons compute only when the spikes do occur, the spiking neural networks can wonderfully achieve higher energy efficiency, better temporal information processing, brain inspired intelligence, compatibility with neuromorphic hardware, etc. Thus, SNNs are becoming more and more popular in robotics, automation, healthcare monitoring, brain computer interfaces, and next generation low powered AI systems. So before that, the game started in 1950s, where the first one is Hebb's rule. The proposal of spiking neural models has just been given, which is given by Hodgkin-Huxley. Then comes the 1970, where an outing gate, the transistor as a synapse axon, back propagation learning and neuromorphic computing was there. Then in 1990s, spiking neurons actually came, followed by HTDP, that is time-dependent plasticity. Long-term potentiation for memory come here in 1990s. Then in 2000, biological mechanism combine HTDP, then followed by neurogrid chip, neuromorphic vision sensors. Then in 2010, digital big brain or True North trained with GPUs has been developed. Then in late 2020s, brain mechanisms neuromorphic data developed the training algorithms for spiking neural networks algorithms for hardware co-design. So the neural models here used are, as I have already said, leaky, integrate, and fire, Hodgkin-Huxley, and SRM models. There are different learning mechanisms such as spike time dependent plasticity, surrogate gradients, and Hebbian learning. The spike encoding strategies are real world analog input is being encoded into spike that trains utilizing biologically inspired techniques. When employing the spiking neural networks with image based data, images must be transformed into binary spike trains. Temporal coding that produces one spike per neuron, and the spike latency is inversely proportional to the pixel intensity. The rate coding actually transforms the pixel intensity into a spike train with the number of spikes proportional to pixel intensity. Then comes direct coding that employs a trainable layer that produces a floating point value at each time step. The layer then turns each pixel at a specific time step into a floating point value, and then a threshold is being applied to the resulting floating point value to select either to 0 or 1. Phase coding encodes temporal information into spike patterns using a global oscillator. Burst encoding transmits spikes into bursts, which improves communication reliability. For vision-based tasks, data from dynamic vision sensors exists in spike format and does not require any extra encoding. So different learning mechanisms, as I have said, to support unsupervised and reward-based learning. This architecture incorporates spike time dependent plasticity, reward modulated STDP, and surrogate gradient descent. In STDP, pair-based STDP rule changes synaptic weights at the local level based on spike. In reward modulated STDP, a third element called the reward signal influences the synaptic updates, allowing reinforcement learning like behavior. The surrogate gradient descent is then used for supervised training tasks to simulate non-differentiable spike functions, allowing for back propagation through time. Then comes different hardware considerations. So before moving to the advantages, let me just re-emphasize the hardware considerations that must be taken into account before working with spiking neural networks. Is that the architecture must be designed to run on neuromorphic devices. Lohi Intel enables local learning and configure synaptic plasticity principles. Brainscale S and TrueNOT uses analog and digital implementation of spiking neural networks to perform energy efficient inference. The architecture is then tailored to certain use cases. Spiking neural networks can be used to recognize gestures on the devious gesture set together with temporal feature learning using RSSN layers. Spiking convolutional layer monitor moving objects with event-based camera input. For motor control, reward modulated STDP adjust weights for learning control sequences for robotic actuators. So how is spiking neural networks is being simulated? Several simulation tools can be created to model and evaluate the big spiking neural networks, each having unique strength in handling large-scale or biologically detailed structures. Brain developed by Romain Bratt and Dan Godman is flexible and user-friendly, making it ideal for quick prototyping of spiking neural networks. General Neural Simulation System, that is Genesis, which was developed in James Browser's laboratory at Caltech, offers a full framework for modeling realistic neural network systems. NEST, managed by Nest Initiative, is designed to simulate large-scale spiking neural networks with efficient parallel computation. Neuron, created principally by Michael Hinz and Ted Carnevale at Yale University and Duke University, specializes in simulating individual neurons and tiny networks using sophisticated compartmental models. Runtime Analysis and Visualization Simulator, created at Bielefeld University of Applied Sciences and Arts, is a runtime tool for analyzing and displaying spike activity during execution. These simulators are essentially crucial for testing and validating different biologically inspired models and learning rules in spiking neural network research. So we can see all these tools and the learning history that has been developed from 1950 back then late 2020s. I have published a review paper regarding that in Evolving Systems. You can, those who are interested can please go through this paper. So there are different advantages, which is energy efficiency, of course, temporal processing, event-driven computation, neuromorphic compatibility, and so on. So what are the challenges? The challenges are training, complexity, hardware limitations, and lack of mature software ecosystems. So coming to the applications, there are diverse applications of spiking neural networks such as robotics, where spiking neural networks are actually prized in robotics for their real-time processing capability of sensory data and accurate motor control. They are actually perfect for systems with limited power because of their event-driven design, which enables them for effective integration with robotic sensors and actuators. Spiking neural networks are used for real-time motor control by utilizing the spiking neural network's capacity to learn spatio-temporal patterns for actions like gripping and walking and controllers for robotic limbs. For example, spike time dependent plasticity is a biologically inspired technique that enables brain controls to adapt to changing settings. There are other recent research progress in robotics such as real-time motor control, sensory matter integration, autonomous navigation, and energy efficiency. Then comes the neuromorphic computing, which I've already said. Then comes real-time sensory processing. Because of their event-driven architecture and capacity to manage temporal dynamics, spiking neural networks are excellent at processing real-time sensory data. They are widely utilized for auditory processing, including speech recognition, sound localization, and auditory scene analysis. For instance, in complicated situations, the spiking neural networks are able to identify sound sources by analyzing the timing and strength of sound spikes, which can be seen from a recent research. Another recent research has shown that spiking neural networks are widely adopted in visionary systems for event-based visual processing, including object detection and tracking when paired with neuromorphic vision sensors. Because they can just process scene changes rather than the full frame, these systems are incredibly efficient. Then comes spiking neural networks are also widely used for tactile sensing in tasks like material recognition and texture analysis in robotics because they can interpret data from tactile sensors to allow robots to perceive and react to physical interactions. By using these spiking neural networks and event-based cameras, robots can immediately identify and react to rapidly moving objects, increasing their operational efficiency. Then comes the spatio-temporal pattern recognition, which is the most important application of spiking neural networks so far. The capacity of spiking neural networks to identify patterns that develop over time and space is one of their most important potent uses. By utilizing their temporal encoding characteristics, spiking neural networks have been effectively used for tasks such as phenome recognition. They analyze time-varying audio signals to find speech patterns, frequently using less energy than conventional techniques. Spiking neural networks are also widely adopted in the analysis of biological signals, including electromyography and electroencephalography, such as EEG. They are ideal for applications such as prosthetic control and brain-computer interfaces because of their capability to detect temporal correlations in spiking data. They are widely used for event detection in surveillance by analyzing event stream in video surveillance system to identify anomalous or questionable activity. Their temporal
Hello,
capacities enable real-time analysis
hello,
of
madam. Am I
dynamic
audible?
environments. Yes, sir.
Hello. By any chance, you are changing the slides? Your slide changes are not visible.
Sir, actually, I'm just elaborating on the applications. I have
Okay, okay, no
kept
problem, no
my
problem, no problem.
slides as short as possible.
Okay, okay, okay. No problem, no problem,
Sir,
no problem.
anything you are not able to follow, you can just tell me, sir.
No,
I'll
no, no, no,
just
no, no. Actually,
recall.
no, 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 no. Actually, what happened that you are explaining, so I thought that there might be some other slides in case. Okay, so that's why I'm asking. Okay, no problem.
Oh,
No.
okay, sir. Okay. Yeah. So coming to the video surveillance systems to identify anomalous or questionable activity. Their temporal capabilities. Then to increase the flexibility and responsiveness of robotic system, recurrent spiking neural networks are widely being developed nowadays. In flexibility and responsiveness of robotic system, recurrent spiking neural networks are being widely adopted to identify dynamic spatial patterns. So there are a lot of research works that are going on in spatio-temporal pattern recognition using these spiking neural networks, which I'm currently working on. But what happens is that their physiologically inspired temporal coding, which allows for real-time processing of dynamic data, is the main benefit of spiking neural network. Real-time gesture control, event-based object tracking, and EEG-based prosthetics are a few examples of different applications. But what is the problem? The problem is that it still exists, such as task-specific encoding is required for the extraction of spatio-temporal features. Scaling training is very challenging in case of spiking neural networks, and adaptability of noise is also an issue. Particularly in audio and brain signals, spiking neural networks is restricted. Although surrogate gradient training and hybrid spiking neural network deep learning systems have been widely adopted nowadays to seek to improve scalability and accuracy, but they are often limited in their deployment readiness and have a high computational cost. Overall, even though spiking neural networks have the ability to comprehend rich temporal data, wider acceptance is still forbidden as it depends on real-world developments in spike encoding, model interpretability, and training efficiency. So now coming to the event-driven nature of spiking neural networks and the neuromorphic hardware. So instead of depending on continuous signals, spiking neural networks information in the form of discontinuous occurrences or spikes. Once a threshold is being crossed, neurons respond to the incoming inputs by producing these spikes. This event-driven paradigm has several important advantages. Most neurons in a spiking neural network stay dormant the majority of the time since they only fire or spike whenever required. In contrast to typical neural networks, which need to be continuously activated throughout each of the time steps, these result in a far smaller computing overhead. By encoding temporal information, spikes in spiking neural networks improve the ability to analyze patterns that changes over time. Real-time sensory processing and other spatio-temporal activities benefit greatly from this nature of spiking neural networks. A large portion of the network is dormant in spiking neural networks since neurons only activate when necessary. This lowers the overall energy usage since the energy consumption is proportionate to the number of spikes rather than the total number of processes. So the neuromorphic hardware, the construction and the operation of these neuromorphic devices are intended to resemble those of the human brain. To support the event-driven architecture of spiking neural networks, the neuromorphic hardware integrates specialized components. It makes use of low power and high performance computing such as spiking neural models where specific circuits on neuromorphic chips such as IBM True North and Intel Lohi mimic the actions of spiking neurons. Extremely efficient computations are made possible by this chip's optimization to handle the sparse event-driven nature of spiking neural networks. Then comes the event-based processing, where rather than processing all the information at once, neuromorphic processors can process the data as discrete events or spikes. This makes it possible to interpret sensory input like visual or oral data in real time while using a lot of less power. Then comes asynchronous communication. Here, neuromorphic processors provide asynchronous communication in contrast to conventional hardware, which processes information in synchronous cycles. Clock synchronization is not necessary for the network to process information because neurons only communicate when they spike. Because there is no longer a requirement for continuous signal transmission across the system, power consumption is further decreased. Then comes the distributed computation, where the neurons in neuromorphic systems are frequently grouped in layers or clusters throughout the chip. Parallel processing is supported by this distributed design, which speeds up the processes like pattern recognition and learning by simulating the biological systems. So these are some of the following high performance computing that are being utilized by the neuromorphic hardware, that is spiking neural models, event based processing, asynchronous communication, and distributed computation, of course. So what is the benefit of this synergy? Significant power savings have been achieved by combining the neuromorphic technology with event-driven computation. The neuromorphic hardware is perfect for edge devices and mobile systems because spiking neural networks processes information asynchronously and only when needed, allowing them to run complicated algorithms with far lower power consumption than traditional digital hardware. Neuromorphic hardware is designed to process events in real time, which is crucial for activities requiring rapid reactions to sensory inputs such as robotic control, visual processing, and oral signal recognition. Neuromorphic systems can accommodate millions of neurons and synapses, supporting massive, intricate spiking neural network models. They are appropriate for wide scale pattern recognition, like in huge sensor networks or driverless cars, due to their scalability. Learning algorithms are being incorporated into many neuromorphic systems, enabling the system to adjust and to get better over time via mechanisms like STDP. Neuromorphic systems can also learn and carry out tasks without requiring significant retraining due to the biologically inspired learning algorithm that adjusts its strength depending on the connections between neurons based on the timing of their spikes. In a recent research, it has been seen that the application of neural network model of the spiking neural network model for real-time sensory data processing demonstrates how it has been widely adopted for various real-time applications. It also provides insights into the combination of spiking neural networks and neuromorphic hardware for applications that require low power, high performance computation, particularly in robotics and sensory systems. So some of the typical example of hardware platforms are Intel Lohi, TrueNOT by IBM, and systems for brain-inspired computing. So now coming to the recent research trends. Deep spiking neural networks, hybrid artificial neural networks, spiking neural network models, and low-powered AI systems are currently being widely adopted more and more by the researchers. So these are some of the research trends where the deep spiking neural networks have widely been adopted for development of deeper architectures comparable to convolutional neural network and transformer. The key techniques that have been widely adopted here is surrogate gradient learning, back propagation through time. These typical applications include image classification and object detection. So what is the advantage of utilizing this architecture? Higher accuracy, of course, and improved feature extraction. Then another research says artificial neural network to spiking neural network conversion, where conversion of pre-trained artificial neural network into spiking neural networks has been done while maintaining the performance. Key techniques that are widely adopted here is rate coding, threshold balancing, and weight normalization. Typical applications include computer vision, speech recognition, and the advantages are reduced training complexity and lower energy consumption. Then comes transformer-based spiking neural networks or speakformers. Here, integration of spike-based computation with transformer architectures is being done. Self-attention mechanisms has been adopted with spike-driven attention mechanisms. Applications are vision transformers and video analysis. Then comes neuromorphic computing, where the deployment of spiking neural networks on specialized hardware platforms is being done through event-driven processing and neuromorphic chips. It is widely adopted in edge AI techniques, IoT devices, and robotic automation. The advantage is that it has got ultra low power consumption. Then comes event-based vision systems where data processing from dynamic vision sensors is done using spikes. The key techniques that are adopted here are event cameras, temporal coding techniques. The applications are autonomous vehicle surveillance. Then comes the advantages such as high speed processing and reduced redundancy. Then comes brain inspired learning. Here, incorporation of biologically plausible learning mechanisms has been done. Key techniques that are widely utilized here is spike time dependent plasticity and Hebbian learning. Applications are cognitive computing, of course, and advantages is that it has got improved biological realism. Then these are some of the recent other research trends as spiking neural networks is getting more and more attention across 2026 and it will remain as popular till 2030s as scientists are predicting, where hybrid artificial neural networks and spiking neural networks are also widely adopted, whereas convolutional neural network has been uh, just hybridized with spiking neural networks using transformer and SNN hybrids. It is widely adopted in medical imaging and speech processing, but the advantage is that it has got balance between accuracy and efficiency. Then another recent research direction is federated and edge spiking neural networks, where distributed training and inference for privacy preserving AI is done. Federated learning edge deployment is adopted as key technologies. Healthcare monitoring and smart cities are the typical applications, and the advantage is, of course, enhanced privacy and low communication cost. Then comes reinforcement learning with spiking neural networks, explainable spiking neural networks. Of course, without explainability, it will remain as black box as that of traditional artificial neural networks, where attention maps and spike visualization are the key technologies. It is widely adopted in medical diagnosis for medical practitioners and doctors. The advantage is that improved transparency and trustworthiness. Then comes spiking graph neural networks, where the integration of graph structures with spiking computation has been done. Graph convolutions, temporal graph learning has been the key technologies over here. Applications are social networks and brain connectivity analysis. Advantage is that it has got efficient processing of graph-based temporal data. Then comes multimodal spiking neural networks, where fusion of multiple sensory inputs using spike-based representation is done. The key technologies that are used are cross-modal learning, healthcare robotics, and advantage is that it has got improved robustness and contextual understanding. So these are some of the recent research trends in spiking neural networks, but of course, it has got its banes too. There are several lacunas and solution directions which scientists have came across is that difficulties with spiking neural network training because SNNs are event-driven and biological neuron models are complicated. Training spiking neural network is far more difficult than training a regular neural network. The main difficulties typically are absence of differentiable activation functions. While spiking neural networks lack differentiable activation functions because of their discrete spiking activity, Traditional neural networks rely on gradient-based optimization techniques such as backpropagation to train on the network. Because of this, traditional backpropagation is challenging to use. A solution can be to adopt gradient-based learning here in spiking neural networks, where researchers are currently investigating surrogate gradient techniques, which uses continuous approximation of the spiking function. Furthermore, training uses biologically plausible learning rules such as STDP. Then comes inefficient training algorithms. This is another research lacuna at this time of spiking neural networks. At this moment, the majority of the spiking neural networks rely on unsupervised learning or biologically inspired principles like spike time dependent plasticity, while useful in being certain situations that might not scale well for big and complicated data sets, particularly where supervised learning is needed. To increase the spiking neural network capacity over here to manage much more challenging tasks, recent development like seek to integrate supervised learning mechanisms are widely utilized here, like spike prop and backpropagation through time, that is BPTT. There are several advanced learning algorithms that our researchers are currently exploring that improve the efficiency of training the spiking neural networks for large-scale applications which involves complicated data sets. Then comes scalability challenges. This is also another important issue of the spiking neural networks, where the computational expense and memory requirement associated with a high number of spikes, neurons, and synapses make scaling the spiking neural networks to huge networks or real-world applications another crucial problem. The complexity of computation is there, where the complexity of handling and processing the enormous number of spikes and synaptic connections increases exponentially with the size of the spiking neural networks. Power consumption and latency may increase significantly as a result. To solve this problem, neuromorphic hardware like IBM's TrueNorth and Intel Lohi is made especially to scale spiking neural networks by enabling asynchronous and massive parallel calculations using low power event driven processing. These platforms provide a hardware level assistance for effective scaling management. Then comes network sparsity and synaptic plasticity. Sparse connections are essentials for managing big spiking neural networks to lessen the computational load. It can be difficult to make sure that spiking neural networks continue to train efficiently when using sparse network and plasticity techniques. What will be the probable solution there to deal with this network sparsity problem? A probable solution can be that learning sparsity patterns and sparse coding techniques, which helps to balance the network size and learning capability, can be a solution. Integrating with hardware platform, where the spiking neural networks must be closely integrated with specific neuromorphic hardware that has to be developed successfully. But there are also certain limitations, like hardware limitations. Despite being designed for event-based computations, neuromorphic hardware may have constraints like processing speed, memory, and connectivity when the complexity increases in spiking neural networks. Mismatch between biological and artificial neurons can also be a problem, where the accuracy of real-world applications can be limited by a mismatch between the complex behavior of real neurons and the simplified models employed in spiking neural networks, even when neuromorphic hardware replicates biological systems. So to improve this hardware integration, researchers are nowadays enhancing the neural models and implementing hybrid learning schemes that blends more reliable machine learning techniques with physiologically relevant mechanisms, as we have come across these recent research trends. Then what are the real-time performance challenges? As spiking neural networks must be able to absorb sensory inputs rapidly and adjust to changing environment in real-time applications like autonomous systems and robotics, However, because this spike-based computation is inherently complicated, real-time performance is frequently difficult to achieve. Such as timing and latency problem is also there, where in applications such as sensory processing or robotic control, real-time performance is essential. System performance may be impacted by delays caused by the timing and latency of spike processing. Neuromorphic circuitry enhances the spike processing and propagation, enabling real-time processing. Furthermore, the sophisticated learning algorithms like STDP are incorporated to enable quick adaptability and instantaneous reactions. The application of spiking neural networks to real-time sensory processing, along with the difficulties in real-time performance and how neuromorphic hardware can help, is nowadays a recent and hot topic in research. Here, spike time dependent integrated coding employs a time varying threshold to augment information capability. Utilizing these approaches, a recent research presented the ultra low latency and highly accurate object detection model. There are other several innovative approaches like surrogate gradients, hardware optimization, and hybrid learning schemes, which we have just came across, are actively addressing the primary problems that SNNs face, such as training difficulties and scalability issues. Hardware integration and achieving real-time performance does not remain a bottleneck nowadays due to these hybrid schemes. These difficulties thus demonstrate how spiking neural network research is still developing and how it might be used to address challenges in real world. So there are also other problems like data augmentation and class rebalancing strategies for handling the dataset imbalance in spiking neural networks, which is substantially difficult, particularly when training on real-world datasets with inherently skewed class distributions. Data imbalance in spiking neural networks can result in biased learning, limited generalization, and low accuracy on minority classes. So to solve this, a variety of solutions have been developed, including data augmentation and cost-sensitive methods for learning. A typical option can be data augmentation techniques can be used prior to or following spike encoding. For framework-based datasets like MNIST or CIFAR10, common image augmentation methods such as rotation, cropping, flipping, and scaling can be used before turning images into spike trains with rate or latency encoding. These pre-processing techniques have been demonstrated to enhance generalization in spiking neural networks formed via artificial neural network to spiking neural network conversion. Augmentation techniques are used directly in the spike domain for event-based data, such as that collected by dynamic vision sensors. These include temporal jittering, such as random spike time shifts, spike deletion or insertion, and the addition of Poisson noise to replicate unpredictability in biological brain responses and improve network durability. So there are certain limitations of spiking neural networks also in comparison to traditional neural networks, which is accuracy, where spiking neural networks frequently underperforms deep neural networks on many standard benchmark datasets, such as image classification, example ImageNet CIFAR10. Spiking neural network shows promising result on event-based dataset, but their accuracy on frame-based dataset often do lags behind. This accuracy gap is caused mostly by the sparse nature of spike-based representations and the low depth of current spiking neural network models. Then comes the training complexity. The spike events are non-differentiable in nature, complicating the spiking neural network training. Surrogate gradient algorithms, ANN to SNN conversion techniques have made improvements, but they do still suffer from convergence stability and frequently require prolonged training times. On the other hand, deep neural networks benefit from well-known backpropagation algorithms and GPU-accelerated libraries. Tooling and ecosystem is also there, where the software ecosystem supporting the spiking neural network development is still in its budding stages. While frameworks like Brian2, Nest, BindsNet, and Knots exist, they are not as robust or well supported as prominent deep learning packages like PyTorch or TensorFlow. This reduces the reproducibility and impedes fast experimentation in spiking neural network research. Then comes the hardware constraints. Though neuromorphic devices provides energy savings, they are not yet as accessible or scalable as traditional
Ma'am,
hardware
am I
experiments.
audible?
Yes, sir.
Ma'am, means since we are quite fine time, ma'am, how much time will it take? Hello, ma'am.
Yes.
Ma'am, am I audible?
Yeah.
Oh, ma'am, I was just saying, means since we are in time, means how much time should we, means there are some questions also. So
Yeah.
in
Yeah.
view
Yeah.
of
Yeah.
time, okay.
You
So
can
ma'am, once,
just give me 2 minutes and I will just conclude.
okay, ma'am, sure, ma'am. Sure. Thank you, ma'am.
Yeah. So, examining the optical or quantum computing for spiking neural networks and other non-conventional computing paradigms can be a solution. Massive parallelism and speed could be offered by these paradigms, allowing for hitherto unheard of real-time SNN computation, particularly for intricate jobs like large-scale pattern recognition or modeling. A recent study has explored the quantum inspired methods for spiking neural networks to improve complicated pattern recognition tasks. Future applications do typically include multi agent robotic exploration, neuromorphic vision systems, and wider implementation in brain computer interfaces. So, notwithstanding with the advancements, issues with co-designing hardware and software, training stability, and attaining deep learning level precision still do exist. So this is just a brief introduction to spiking neural network and how it is revolutionizing the future of brain-inspired AI. So over to the audience. If any question, you are always welcome. Thank you, sir.
Thank you very much, madam, for your wonderful talk. So we can see one question from Mr. Moinak Sen from the audience. Can you please share the libraries we can use to implement SNN? And the next question from him.
Yes, yes, yes.
So please, you can answer his first question for. Okay, so then I will read out the next one. Hmm. So you can write his
Sir,
answer
can
in
you
the
just
chat window.
okay, sir? Is it fine if I write in the chat window?
Sure, sure. Please, 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 please feel free to write his
Okay.
answer to the chat window. Or if you have any resource link, you can share with him.
Actually, the audiences are requested to go through a recent review paper of mine, which has been recently been published in the mid 2026 spiking neural networks, a comprehensive research review of diverse applications, research progress, challenges, and future research directions. Here, each and every resources, the timeline, challenges, recent application research trends are being shared over here. You can just go through it, and if required I can share with you in WhatsApp or by mail, whatever is as per convenience. So now, coming to the question, so the Meenak, what is your question? Can you please? I'm not able to see. Yes, yes, yes. Seen. Can you please share the libraries we can use to implement spiking neural networks? Do you always need to have a neuromorphic hardware or not? No, neuromorphic hardware not always requirement is essential because it depends on the real-time applications, on which application you are actually implementing the spiking neural networks. So of course, having a neuromorphic hardware is not always essential. It depends on the real-time applications you want to solve. And coming on to the libraries we can use to implement the spiking neural networks, the answer is actually quite long. I can share the resources with you just a few minutes after the slide. So coming to the next question, what is the strongest evidence then that spiking not just neural networks is essential for intelligent behavior? So this is actually, as we know, that spiking neural networks is a breakthrough in artificial intelligence, which is inspired by the event-driven and temporal dynamics of brain-inspired systems. It is as opposed to conventional artificial neural networks. It uses discrete spikes to process information, allowing for energy-efficient computing and the native handling of sequential and temporal data. And
Okay, thank you, madam.
so, Munakshan, I'll be just shortly sharing with you all the libraries.
Ma'am, you can share it with me. I can share it with all the participants, the PPT
Yes,
as
yes,
well
yes.
as the resources.
So it is very much important, madam. So kindly share the PPT with us also, so that we can
Sure,
email.
sir,
We can also email with the participants. Huh?
sure, sir, sure. I shall share very soon.
Thank you, madam.
Okay. So, Shabashita, do you have any other questions?
No, I can't see any other question from the chat window. So if you,
So,
so I think it is the time for group photo. I guess participants do
yeah,
not
yeah,
have any other
yeah.
questions.
So, can I just request everyone, means who are interested, to kindly turn on your camera so that we can have a short group photo together.
Actually, it is not possible to open my camera. I am in a lab. Okay. Through the
No,
desktop,
no
I
problem,
have
sir.
joined.
No problem, Mr.
No
Amita.
problem,
No
no problem.
problem. Thank you very much for joining the session in spite of your busy schedule. Thank you very much.
Okay. Okay.
Ma'am,
Thank you.
Parijata, ma'am, I also request you to kindly, if you can, turn on your camera for the snapshot for a second.
Santosh da, how are you?
Parijata, ma'am, am I audible?
So Rajiv, let's not force anyone. So let us
Oh,
take
ma'am,
the
yeah,
group photo.
yeah,
Let us take the
ma'am
group
has
photo.
turned,
We might have any
ma'am has
problem.
taken,
Ah,
ma'am has turned on the camera. So I will just take a photo.
oh, sure.
Okay. So kindly everybody say cheese. Just a second. Yeah, thank you.
Thank you everyone for joining the session. Thanks to
Thank you.
Parijata madam for her wonderful talk and sharing her valuable time with us. So I think it's time for sharing the memento and wrap
Yeah,
up the session.
yeah, I will just share my screen.
Kindly share your screen and share the memento with her.
So, ma'am, on behalf of Complete Computer Society IEEE Kharagpur branch, as well as IEEE Kharagpur section and student branch, as well as IEEE India Council, we'd like to share you a small piece of token of appreciation from our end. So, as a part of the session. So, uh, apart from this, I will just try to mail you the complete thing just after the session is done. So, yeah, thank you, ma'am.
Thank you so much for just inviting me, and it was a very wonderful session to interact with you all. And this is my first opportunity having been invited among all these esteemed faculty members from IIT Kharagpur. So thank you very much for giving me this opportunity, and please count me in for all such future opportunities as well. Thank you, Shubhashri sir. Thank you, Rajdeep. Thank you,
Thank you.
everyone.
Thank you, ma'am. Thank you, ma'am.
Thank you, madam. Thank you.
Okay, so thank you everyone for joining for today's session. I hope you liked the session. You will be getting notification of future sessions soon. So stay connected to us through the WhatsApp group that we have, if not connected till now. Also, you will getting email notifications. Yeah. Thank you. Thank you, Shobhana. Thank you.
Thank you, Rajiv. Bye.
Bye bye.
Good night.
So, Rajiv, have you captured the memento picture? I think Rajiv has logged out. No problem. No problem, Santosh. I can understand you are traveling. No problem at all. Thank you very much for joining.